All right, so part 2 of 11.10, here we have in your notes a list of some important Maclaurin series. We've already looked at the e to the x. Here's our 1 over 1 minus x, our geometric series. We did the cosine of x, the negative 1 to the n times x to the 2n over 2n factorial. And then they also tell us what their radius of convergence is. So again, if you have to, we can use this as reference material, a lot like our integration tables. All right, so this is something we want to keep with us throughout the sections of the homework. All right, the last one I want to point out this goofy notation here. This is for a binomial series where k over n is defined as k times k minus 1 times k minus 2 all the way down to k minus n plus 1. All over n factorial. This represents your binomial coefficients that are going to be in front of your x's here. Okay, so that's what all these fractions stand for. That's what this notation here represents. All right, so example 5. Use the Maclaurin series in the table to obtain a Maclaurin series for the given function. F of x equals x squared times natural log of 1 plus x to the third. All right, so this looks a lot like your natural log of 1 plus x. So we're going to take this and we're going to tweak it a little bit. All right, so we're going to take this x to the third, and it represents every x in our series. So we're going to replace that with all the x's. So this x to the n is now x to the third to the n. All right, so that becomes x to the 3n. And you still have this x squared being multiplied out front, which means you just have to multiply the x squared to your x to the 3n. Well, again, when you multiply like bases, you add your exponents, and that gives us x to the 3n plus 2. And there's the Maclaurin series for this particular function. All right, example 6. Use the Maclaurin series in the table to obtain a Maclaurin series for the given function. We have e to the x plus 2 times e to the negative x. So I see 2e to the x's here. So quick, let's go steal this from our table. All right, so that represents the e to the x, and then we'll finagle this one to look like these by putting just a negative x in all those spots. So here's the first summation. That represents our first e to the x. And then we're going to add to it a 2. Then the summation again, but now we put in negative x in for the x. Raise it to the nth power. All right, so we're going to manipulate this part because we can probably combine this together. So let's take the negative off of the x and call it negative 1 to the n power. And we can bring the 2 onto the inside. Reason being is because now both of these summations have the same denominator. So we're going to be able to add the numerators together when we're done. And again, we have our x to the n here. So adding those two fractions together, x to the n plus 2 times x to the n times negative 1 to the n. Well, a reason I put these two together, the 2 and the x to the n power, is because these are two terms separated by the plus sign, so I can factor out the x to the n out of both of these. So this becomes x to the n now times 1 plus 2 times the negative 1 to the nth power, all over n factorial. And there is my Maclaurin series. Example 7. Let's use the Maclaurin series in the table to obtain a Maclaurin series for the given function. We have f of x equals the square root of 1 plus x. So let's change this to 1 plus x raised to the 1/2 power, and looking through our table, that's our binomial series, 1 plus x raised to some k power. In this case, k is going to be 1/2. So we'll put 1/2 every place where we see a k. So we're going to start right here. All right, so that's going to give me 1. Again, you put 0 in for n. That becomes 1. And if we look over here, that's the first number of our series. Then we put in the 1 half in for k times x. And then we're going to have 1 half times 1 half minus 1, which is negative 1 half over the 2 factorial times x squared. 1 half times 1 half minus 1. That's going to be the same negative 1 half. Now, 1 half minus 2, that'll be a negative 3 halves. All right, so starting to clean, I think I got my clicks out of order here, but cleaning this one up here, 1 half times negative 1 half, that's going to give me a negative 1/4, but I want to keep everything with 2's here. So I'm going to keep that denominator 4 as 2 squared and put that down below right here. Then over here, I'm going to do the same thing. 1 times negative 1 times negative 3, that's going to be a plus 3. And the 2 times 2 times 2 in the denominator will give me 2 to the third in the denominator with my 3 factorial. And my x to the third stays up in the numerator. So I'm starting to see a pattern. Again, we see alternating signs. So next should be a minus. So if we think k minus 3, 1 half minus 3, that's going to be a negative 5 halves. So that's going to be the 3 times the 5, and there's the minus out in front. And the pattern I see in the bottom, 2 squared, 2 factorial, 3 to the third, 3 factorial, so 2 to the fourth, 4 factorial. Next, we're going to have a 5 factorial. But let's see, that would be now 1 half minus 4. So that would be a negative 7 halves. So the negative times this negative changes it to a plus, giving me a 7. So I'm starting to see the sequence of odd numbers being multiplied together here. And I see my pattern in the denominator staying the same. And we can do this again. Yep, 1 half minus 5 will give me a 9, but a negative 9 halves, if you will. So multiplication of the negative. And there's my 2 to the 6. So everything is following suit of my pattern. So I see patterns here, not with this one. So I'm going to leave off the first 2 terms and find a pattern to create a summation, now starting when n is equal to 2. All right, so let's look through this to find a pattern. Well, here's 2, 2, and a 2. 3, 3, 3. 4, 4, 4. 5, 5, 5. Can't count this 5. 6, 6, 6. So there's part of my summation right now. So 2 to the n times n factorial, x to the n. Let's fix the negative. We want our second term to be negative, so negative 1 to the 2 power. Well, nope, that'll make it positive, so 2 minus 1 will make it negative. And now what we got to do is we got to work with this 3, the 5, the 7, and that's going to be my sequence of odd numbers. So now when n is 6, I need to make a 9 here. So 2 times 6 is 12 minus 3 is 9. When I need a 7, n is 5. 2 times 5 is 10, minus 3 is 7. When I need this 5 right here, 2 times 4 is 8, minus 3 is the 5. When I need this 3, that's 2 times 3 is 6, minus 3 is 3. So here's going to be my pattern, all right, for my odd numbers. Well, what we want to do is we want to turn this into a factorial. Whoa, wait a minute. If we do turn that into a factorial, then the even numbers are going to show up. So then we have to create a factorial to cancel and divide out the even numbers from our factorial. So we want to be able to cancel out the 4, the 6s, the 8s, and so on and so forth. So my first 3 terms I don't want to use this for the 1. I'll explain this in a second. We're going to take this one out. So minus x squared over 4 times 2 factorial is 8. We want to start this now when n is equal to the 3, not when n is equal to 2, and here's the reason. In the denominator is going to be this factorial, which creates the 4, the 6, the 8, the 10, and so on. If we did include this starting at n equals 2, then 2 minus 2 would give me a 0, which is 1, and then I'd have a 2 that I don't want. So starting with the 3 minus 2 is 1 factorial times this 2. So now that's the 2 we want. Then when n is going to be 4, 4 minus 2 will be 2 factorial times the 2. And that will give us the even numbers that we're looking for to cancel out. So if we had to, we could write this all out, and you could see how now I would be canceling out. So again, 3 times 2 is 6, minus 3 is 3 factorial. That would be 1 times 2 times 3, and 3 minus 2 is 1 factorial, which is 1 times 2 is 2. That cancels that 2 up there. And if you check this out as you keep putting in your n's, you will see that this cancels out the even factorials. All right, so there was my Maclaurin series. Darn this mouse, I tell you. So sometimes you have to list out a couple terms until you can find the pattern that you want. All right. Number 8, use the Maclaurin series in the table to obtain a Maclaurin series for the given function and write out the first 5 terms. All right, f of x equals e to the negative 3x, so I'm thinking e to the x right away. So to change this, we've just got to put negative 3x into our summation. So we put negative 3x here, then this x becomes negative 3x to the n power. And again, we probably want to factor out the negative, so negative 1 to the n, and now this becomes 3 to the n times x to the n. So this part right here is going to be my coefficients in front of my x's. So if we write out the first 5 terms, when n is 0, 0 factorial is 1, x to the 0 is 1, 3 to the 0 is 1, negative 1 to the 0 is 1, so these are all a 1. First number. When n is 1, now it's going to be a negative. 3 to the first is 3, x to the first is x, and then you have 1 factorial, which is 1. Then we put in the 2 for all the n's. So that's going to give me 3 squared, and remember our signs are going to alternate now, so we don't have to worry about the negative 1. 3 squared times x squared over 2 factorial minus, then we're going to have 3 to the third, x to the third, 3 factorial, plus 3 to the fourth, x to the fourth, 4 factorial, then minus, but these are your first 5 terms. And so you can start to simplify. 9 squared is 9x squared, 2 factorial, 2, minus 20, oops, wait a minute, we're going to be able to reduce this. 27 over 6 reduces to 9 over 2. Then 3 to the fourth times x to the fourth over 4 factorial. Again, you'll be able to cancel out a 3. So 27 x to the fourth, then 4 times 2 times 1 is 8. And so there's our first 5 terms with everything simplified out. Example 9, find the Taylor series of f of x equals sine of x with it centered at a equals pi over 2. So again, write down your Taylor series, f of x, and let's build a table, start filling in some of our numbers. We can put in our a, which is pi over 2. But now we have to figure out what's this f, what's our values going to be here, right? So let's go figure that out. So n is 0. Our normal function sine of x, sine of 0 is 1. Excuse me, not sine of 0. Sine of pi over 2. My apologies. So sine of pi over 2 is 1. When n is 1, take the derivative of sine of x. That's cosine of x. Cosine of pi over 2. is going to be 0. Take the derivative cosine of x is negative sine of x. Negative sine of x of pi over 2 is negative 1. So again, we have this alternating signs where we come right back to where we started. So let's start to fill in our terms. So f of pi over 2 plus f prime of pi over 2 times x minus pi over 2 to the first over 1 factorial. Then plus f double prime pi over 2. We just fill this out according to our formula here. And we'll list out those terms, and now let's plug in the values. F of pi over 2 is 1. F prime of pi over 2 is 0. Here come those zeros again. Then this is going to be a negative 1. X minus pi over 2 squared over 2 pi. Then the 0. Then plus 1 for when n is 4. X minus pi over 2 raised to the 4th over 4 factorial. Again, plus a 0. Then it's going to be a negative 1. X minus pi over 2, 6 to the 6th power over 6 factorial. So there's our pattern. So when n is equal to 0, there's 1, here's 2, here's 3. We're going to take out the zeros to create just these terms. So this is going to be our summation of negative 1. Now, n is 0, we want it to be positive, so to the n. Then when n is 2, when n is 1, negative 1 makes it negative. Then we have 2 times n, so that gives us that even power. And then 2 factorial is 2 times 1, that gives us 2 factorial. When n is 2, 2 times 2 is 4 for the power, and 4 in the factorial, and that gives us a positive term, so that works the rest of the way. And that ends 1110, part 2.